Chapter 2.4 is more about induction, so we're just doing the same sorts of things with swapping out our numbers with m-1 and basically solving from there. But it's getting a little bit more complicated where you have to do a lot more algebraic manipulation, so it's important that you go slow and do step by step. So in this chapter, we're doing sums as recursive sequences and other uses of induction, and it covers the fundamental theorem of arithmetic. So this theorem is pretty simple. It's just saying that every integer greater than 1 can be expressed as the product of a list of prime numbers. So this is what you learned in algebra when you were basically factoring things down to their simplest parts. So for example, 4 can be factored down to 2 times 2, 5 is just 5, 6 is 2 times 3, and so on. So everything can be expressed as prime numbers if you break it all down. So in the last chapter, we were proving that the result of a summation at each step was equivalent to some closed formula. So we were able to show that if I went from 1 to 1, it would equal this. If it went from 1 to 2, it would equal this. If it went to 1 to 3, it would equal this. So we were just proving that no matter which n you chose, the result of this summation right here would equal the same thing as our n squared. So this time it's similar, we're just working with recurrence relations, aka recursive formulas instead. So example 1 from the book, it has the same 2i minus 1, just like we did before with n squared. We have 2i minus 1, and it gave us another way of writing it as 1 plus 3 plus 5 plus up until 2n minus 1, which would be at position n, the I gets replaced with the n. So it's telling us to use the notation s sub n to denote this sum. So when we write s sub 5, that would be 5 steps. From 1 to 5, we'd end up having 1, 3, 5, 7, and 9. So then we have to find a recursive description of s sub n. So let's just go through this. The first step is to get all the values from 1 to n minus 1 for the summation. In this case, we would write it as s sub n minus 1. And then we express the summation as the sum of the first n minus 1 terms and then the final term. So we have the sum from I equals 1 to n of 2i minus 1. And then we can express this as the sum from I equals 1 to n minus 1 of 2i minus 1 plus whatever this final term is at the position n. So we would have plus 2n minus 1. And that's what we have over here. Oops. So we could write it like this, or we could write it like 1 plus 3 plus 5 plus ... plus 2n minus 3, which would be the value when we plug in 2n minus 1 minus 1. Or if we want to keep it really, really simple, remember that we're using s sub some number to represent these sums now, so this could just be swapped out with s sub n minus 1 plus our 2n minus 1. So now we essentially have our recurrence relation. So let's rewrite this as s sub n is equal to s sub n minus 1 plus 2n minus 1. And that would be the result. But remember that we also need a starting value. So to do that, we just look at this for I equals 1 until 1. Then we plug that in. 2 times 1 minus 1 is equal to 1. So we have this part of the recursive relationship, and then we also say s sub 1 is equal to 1. So don't forget that you also need the starting point, otherwise we don't know what this will be when we start actually generating our number sequence. And this slide just summarizes that as well. So we just plug in I equals 1, we go from 1 to 1, we essentially just plug that in, and we get 1. So for, in this case, this formula, s sub 1, the very first term will be 1. So here's the final result. The recursive formula that shows this summation will be s sub n is equal to the previous term plus 2n minus 1, where the first term is 1. So let's look at example 6 from the book as well. We have n cubed plus 2n is divisible by 3 for all positive integers of n, so 3 times some integer. So we'll just write it that way for now. That's kind of the form we're going to want to end up with. But right now we have this. And we're writing this as d of n is equal to n cubed plus 2n. And remember, if you're stuck and not sure what to do for the starting point, just remember to plug in 1. So checking for 1 equals 1 cubed plus 2 times 1, which will just be 3, and that checks out. It is divisible by 3. So we've at least checked it for the very first term, and then we are going to assume that we've checked it for all terms up through d of m minus 1. So the way we generally will write this in English is that we've checked d of 1 through d of m minus 1. So we've checked that these are true. We're basically saying that this is 3 times some int. So that's just part of kind of the English part of the proof. But this will come in handy later, so just remember this. This is 3 times some integer. Okay, so now let's also plug d m minus 1 into this part. So this is d of n. So d of m minus 1 is going to be m minus 1 cubed plus 2 times m minus 1. And we could do all the math and FOIL that out, but we'll end up with m cubed minus 3m squared plus 3m minus 1. And then if we just distribute that, we get plus 2m minus 2. So this part is the part where it's a little bit tricky to see what happens next. I'm going to rewrite these so that m cubed and 2m are together, which form this original equation. So d of m minus 1 is equal to, I'm just going to put these in parentheses just to show that they're together, m cubed plus 2m, and then write everything else out. So minus 3m squared plus 3m minus 1, minus 3, because we're going to combine these two like terms, but we're not combining these two, because I specifically wanted to write this out. And this is equivalent to d of m. So we're going to take this a step further, and we're going to say that d of m minus 1 is equal to d of m minus the rest of this part. So 3m squared plus 3m minus 3. And now I'm going to write this in terms of d of m. So remember when we were solving like y equals x, blah, 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 and we're solving for x, we have to isolate it. So I'm going to move this whole part to this other side. So to do that, we have to basically subtract this whole thing, and that's just algebraic stuff. So d of m is going to equal d of m minus 1 plus 3m squared minus 3m plus 3. Okay, now here's the other tricky part here. We've already said that d of m minus 1 is divisible by 3. We've already stated that as part of the proof. So now, similar to how we've been doing in previous chapters when we say that x is divisible by 3, whenever we say this in previous proofs, we would then replace it with something like 3k. Well, we've already stated that d of m minus 1 is divisible by 3, so we are going to be replacing it with 3k. So d of m is equal to some odd number plus 3m squared minus 3m plus 3. Then finally we can factor out this common 3, so d of m is equal to 3 times k plus m squared minus m plus 1. So now we finally have our proof that d of m is divisible by 3 for any integer plugged in. So this right here is the proof. So in these slides, we're isolating it out, and then finally we have the same form. We're replacing it with 3k and factoring out the 3. So by doing some creative algebra, we can end up solving this by induction. But you really have to take it step by step, figure out ahead of time what you're kind of going for. We know that whenever we're proving that something is divisible by 3, we're going to end up with some sort of 3 times some value. So at least we had some rough idea of what we wanted to get out, and then we just have to go from there. So remember to solve for the first term first, and then for the penultimate term, essentially, the m-1 as the second part, and remember to try to get this back out. So it'll be a little bit more helpful, I think, if we go through more textbook examples and just kind of show the steps over and over, and hopefully that will make it a little bit easier to follow. Okay, so the first problem from the textbook in this chapter is to take this summation and represent it as a recurrence relation, or otherwise known as a recursive formula. So let's just figure out what a sub 1 is first. So remember, this is just another way of writing our summation. But if we have a sub 1, we're going to have 2, and this first index here is going to be what we have at that point. You can kind of tell what the value of the exponent is based on the index here, because it only goes up to n-1, and also because this starts at 0. So obviously this is going to be n-1 if we're starting at 1, so 0. And so this results, this is 1, so this equals 2. So we have our first term of our recursive formula. Okay, so now let's think about a sub m-1. Well, this is going to be the values from n is 1 until this point, if we're just kind of thinking of it graphically. And then this would be the final term for a is equal to n. So if we are writing this formula as a sub m, it's going to be the result of a sub m-1 plus the final value. So this will be 2 times 3 to the n-1, like this. And this is the result. So this is how we would write our recurrence relation. Okay, let's look at the next one. So if you're feeling lost at this point, remember, just do the first term first. So c sub 1 is going to end up being this very first thing. It will end up being 1 over 2, 1/2. And we can already see the formula going here. It's n and then n plus 1. So let's think of this as c of m is equal to cm-1, so up through this part, plus the very last term, this part. So this will be 1 over n plus 1. And then this whole thing is the final version. So really, this part's not too hard. We're not guessing what the relationship is. We're figuring it out by using induction. And so we have c of m-1, and I forgot to write those as m's, or you can write these as c of n, cn-1 plus n plus 1. And this is what the answers have in the back. So then the second set of questions in the book refer back to the first set of questions. So this one says, show that a sub n is equal to 3 to the n minus 1 for all positive integers n. So this is a closed formula, and then up here we have our recursive, where we have this part as well. So first step, again, just look at the first term. A sub 1 is 2, so let's look at what a sub 1 is when we plug this in. 3 to the first minus 1. That's 3 minus 1, which is 2. So that first part checks out. And then we start thinking about m-1. So in the proof we state that it has checked out for 1, 2, 3, up through m-1. That's just how we write the proof. But now we'll actually use this. So a sub m-1 is equal to, and we just plug it in, 3 to the m-1 plus minus 1. So this is what we have for m-1. Now we look at the recursive formula again. So the recursive formula is a sub m is equal to a sub m-1 plus 2 times 3 to the n-1. So this is the closed formula that we've plugged m minus 1 into, and now we're going to plug it into the recursive formula now that we've found this value. So once we put this all together, we get a sub m is equal to 3m minus 1 minus 1 plus 2 times 3 to the n minus 1. So this is also similar to the previous chapter, where we were using a sub m minus 1 to get a formula to plug into a different formula. So this is what we get here, then we can start simplifying it. So this is where some old algebra comes in, some laws of exponents. Let's rewrite this as 3m minus 1 plus 2 3m minus 1, and I keep mixing up my letters, sorry, minus 1. So if we had x plus 2x, that would be equal to 3x, right? So it's a little bit harder to see in this case, but I'm going to rewrite this as 3 times 3m minus 1. Again, if we pretend this whole thing is x, and this is x, x plus 2x is 3x. And then from the rules of exponents, 3 to the m minus 1 is equal to 3m times 3 to the negative 1. And then we have this 3 on the outside. And this is equal to 3m over 3. And don't forget to bring this negative 1 down the entire way. And then these cancel out, so we end up with a sub m is equal to 3 to the m minus 1. Okay? So then we go back up here. A sub n is equal to 3 to the n minus 1. So this is our result, and that completes the induction. Okay, and let's look at the C part as well. So we already solved 1C, and we got a recursive formula. So 2C says to show that C sub n is equal to this formula for all positive values of n. So again, where do we start? We start with the very first term. We know that C sub 1 should be 1/2. So here we'll plug in C sub 1. That will be 1 over 1 plus 1, which is 1/2, so that part checks out. And then we start thinking in terms of m minus 1. So C sub m minus 1, using this formula here, will be m minus 1 over m minus 1 plus 1. And let's simplify that a little bit. M minus 1 over m. So this is the value of C sub m minus 1, and we can plug it into our recursive formula. So C of m, remember this is the recursive, is equal to m minus 1 over m plus m times m plus 1. I'm putting the denominator first here. So that is what we're going to have to solve to try to get back to this form. So great, we get to work with some fractions, which is always great because we have to do so much work just to deal with the fractions. Okay, so if we want a common denominator, this one already has the m like this. This side needs to be multiplied by m plus 1 over m plus 1. And so let's just go ahead and do that. We'll end up with m minus 1 times m plus 1. And then we'll have plus 1 from this other fraction. And then the denominator will be m times m plus 1. Okay, so let's FOIL this out. M squared plus m minus m minus 1, and then this plus 1 at the end here, over m times m plus 1. So these cancel out, how handy. Let's not skip any really big steps. I know we can see that we're already going to cancel some more stuff out, but let's go ahead and write this out. M plus 1, and we can see that this cancels out, so that would be m over m plus 1. Now we have this form, and that's how our proof works. Okay, let's look at question 4a from the book. This is similar to one I did earlier with the lecture slides, where we kind of had to do some really weird steps to get it to be proven. So remember, the weird steps were one, we acknowledge that p of m minus 1 is an even number. And for the other one, it was divisible by 3. So in this case, we're going to say it's 2k. And we'll swap this out later in the problem. But we're also going to write it as p of m is equal to p of m minus 1, and then some other stuff. So those are the two main things to remember that we're going to do. And we'll see that in a minute. But remember for now, when you're not sure where to start, always start at 1. So let's look at p of 1 is equal to 1 squared minus 1, which is going to be 0. And I guess that's 2 times some number, so that one checks out according to the book. And then next we want to look at for m minus 1. So p of m minus 1, we already know this is even, but that will come into play later. P of m minus 1 is going to be m minus 1 squared minus m minus 1. Remember to put this in parentheses because this subtraction will have to distribute to both of these later on. Now for me, I don't usually like to skip steps in simple algebra, so I'm going to write m minus 1, and just FOIL this out, because otherwise I tend to make really dumb little algebraic mistakes. So this is going to be m squared, and then minus m plus 1, so that's that factored out, so let's write that over here. P of m minus 1 is equal to m squared minus 2m plus 1, and then distribute this negative sign, so minus m plus 1. So at this point, I'm not going to simplify further. This is where we rearrange the numbers to try to get back to our original form here. So I'm going to say p of m minus 1 is equal to m squared. And we're going to take this minus m, so minus m. I'm just going to kind of contain that. Then what we have left over is minus 2m, and then we'll just add these two, plus 2. So this part and this part match. We can write this as p of m minus 1 is equal to p of m, and then some other things, 2m plus 2. And then here's where we're solving for p of m. So p of m is equal to p of m minus 1, and then this part gets moved to the opposite side, so that ends up being plus 2m minus 2. So again, if you don't remember the algebra super well, let's say we had x equals y plus 2, and if we wanted to solve for y, we have to subtract 2 from both sides, and then we'd have y is equal to x minus 2. So it's just that kind of really basic algebra. We're just rewriting it in terms of p of m. And again, remember p of m minus 1, as well as p of 1, p of 2, all of these, per the proof, have been pre-proven to be even. So we're going to end up replacing this p of m minus 1 with a 2k. So let's just write this as p of m is equal to 2k plus 2m minus 2. And then the next step is we can finally factor this 2 out and just say k plus m minus 1. And then that's the proof right there. We get 2 times some number, 2 times some integer, and this ends up being even. So we have proven that n squared minus n is even for all integers where n is greater than or equal to 1. So that checks out as well.